Gary Pokodner from the FAA. Gary, are you online, sir?
I'm online. Gary Pokodner. I am the FAA's program manager for the weather technology in the cockpit program, which is affectionately known to most people as the WTIC program. What you're going to find in this briefing, what I'm trying to do is give everybody here some updates on a number of projects that we have going on that, in my mind, relate to rotorcraft operations. Some cases, they may also impact UAV, their GA. Some of them are specifically rotorcraft, others, I think, just touch them. My intent here is not to go into great detail on each project because I know it's a broad audience and it would take too long of a briefing. I am hoping I can encourage people to request copies of presentations. I have an email at the end. You can request briefings. You could certainly set up telecons with us to go in details. And certainly at the end of this, if there's time, I'd be happy to answer some questions. But overall, I'm hoping this just gives everybody a feel for the number of projects we have going on in the research area. And this project, it actually is, I don't know if Rex did it intentionally, but I think you'll see going after the other two briefings, I kind of am in a good spot here because we're very cockpit and pilot focused and centric versus generically weather. And I think you'll see a lot of the projects and things we're doing are both consistent and complementary to some of the things you've already heard. So go to the next slide. So I'm going to start out, and I'm not going to brief these in any detail. I'm just going to kind of step through them really fast. But what I wanted to show is where the WTIC program typically starts is we do gap analyses. And I know this group and other things that Rex work have done and sliced and diced data in a variety of ways. So I kind of replicated, this is work that was done by the Center of Excellence for GA for the FAA, which is called PEGASAS. So there's some charts here, and again, I won't go through them. You can go to the next one, but they're showing where accidents occur by industry. This one, you'll see the types. You can see obviously wind and visibility dominates. If you look at the chart on the right, you'll see how, and this was what Matthias touched on, how much seasonal effects come into play. That's another way of looking at these and trying to find trends and gaps. And that obviously the most impactful weather events, whether relative to rotorcraft or wind and visibility. So you can go to the next one. This is also just more of the slicing and dicing we did to identify gaps and places to look at, going through data, part of our literature review. And you can take a look at these if you want. Rex has these charts, but again, I think these have been briefed in a variety of ways. So you can go to the next chart. We also did, as part of this, a pilot survey. This gives you some of the results. If this has an interest, we do have some reports available. You can, again, at the end, my email is there if you have an interest in seeing in more detail some of the findings. That report is a better way. This gives you a lot of stats and numbers, things like how many tools pilots are using, what they think of the weather information, what kind of training they've had. So you can kind of see a summary on places, again, that we continue to look for gaps and issues. So go to the next chart. So some of the key takeaways, though, that we found as we did these pilot interviews were current themes where they did complain about coarse or missing weather information, that the weather information wasn't as refined as enough, and there were places they just weren't getting it. There were complaints of failures of weather technology that could be dropouts of data, the technology itself not working. It can be human factors. We got a variety of issues with the technology. Some pilots cited that they thought there's over-reliance on the technology, willingness to self-assess and use decision gates, kind of that they made their own assessments on goes and no-goes and weren't contacting other ways or using outside resources to come to some of these decisions. There's always, and you hear this a lot with rotorcraft, reliance on local or tribal weather knowledge, which I kind of could summarize, I guess, tricks of the trade. If you don't have information, you come up with ways to try to keep yourself safe based on either somebody giving you a tip in the past or your own local experience. And then there's still come up with, there are effects of external pressures on weather-related decision-making. And I think anybody who flies for a number of ways has probably experienced that, as well as some public accidents and all seem to have elements of that may have been impacting or the decisions that got made. So these were some of the key takeaways that we found in doing the lit reviews and our gap analysis. If you go to the next chart, these are the specific gaps that we're now starting to work. I know it's kind of an eye chart. Again, these charts are available. What I wanted to sort of remind people for haven't heard me brief much, what the WTIC program does is we try to target gaps. We bring things down to a small level of a problem that we feel we can control and solve, which is much easier than saying, oh, we want to improve the accident rate or efficiency, where it's very hard to show measures. So if you read through these, you'll see the various gaps that we're trying to address. And for the WTIC program, a gap is simply identified as the difference between where we are today and where we want to be. And trying to get to that point we want to be is the gap that we're trying to fix. So the only one I'm going to talk here about, just because it's the next slide, just to kind of give you an idea of how these gaps relate to some of the research you're going to see, is you'll see towards the bottom on the left, human weather interface, that in many places, basically the pilots are using automated self-briefings more than they are calling now that they've switched to electronic briefings. And that's been a trend, and that's been cited. So now if you look, we started, go to the next chart. So one of our research efforts right now is to assess the effectiveness of self-briefings. And the drivers on this is we're trying to get recommendations for pilot training on performing them, understanding the implications of the shift from flight service, weather briefings to self-briefings. And this isn't always, if you think about it, a lot of this has occurred just because of people getting comfortable and used to technology. It's not like anybody really sat down and determined, wow, self-briefings are really a lot superior. Pilots get more info, it's keeping them safer. It really was just a trend of the world to use your iPads and your phones to get it. It's faster, it's convenient. But it sort of just, it was a natural shift and an evolution. It wasn't necessarily a conscious decision of improvement. So we're trying to take a look at that. Identification of possible performance gaps in GA pilot weather self-briefings, including the use of apps. Are there issues with the systems themselves? Are there places where pilots think they know what they're doing on the self-briefings and they're making errors in interpreting the information? Because again, you're operating on your own. You don't have somebody else there cross-checking you. And then we want to come up with recommendations. Again, we use the expression minimum weather service. Every system designed for self-briefing certainly doesn't need to be the same. People have different preferences, but you do want to make sure that a system designed for briefing you on weather is comprehensive, complete, and gives you the information you need in a convenient, easy to understand method, and reduces the risk of errors. So those are some of the drivers. If you go to the next chart. Research areas, they kind of parallel what the drivers are. We're trying to find out how well pilots are training on self-briefings. Do they understand the implications? Can we get that and see what really happens when you move away from having a professional briefer to self-briefing? Are there gaps there? Are there things that aren't happening that used to actually be safer? Is it better? What are the differences? Identification of possible performance gaps in the self-briefing, we're hoping to identify to continue to enhance that. And then ultimately, our goal is recommendations for system designs, as well as instructions for self-briefings. Can we make this more effective? And people have seen this briefing before, but we presented to this group and a number of other groups knowledge tests that the WTIC program ran for various pilots. And if people remember, scores were very low. At best, professional pilots were around the 70%. A lot of GA were down around 50%. So there is concern that you don't know what you don't know, and that you may look at these self-briefings and think you're doing them right and interpreting them correct, but there may be gaps that pilots are missing. So we're going to try to highlight those and find ways to make sure those gaps get closed. Next one. And then finally, the outputs for this project in particular are, we want to get that comparison between the performance of doing a self-briefing and a flight service briefing. We want to also develop scenarios and performance measures that we can use for subsequent studies. We want this to be adaptable as things continue to evolve. So we're hoping to have good scenarios we can continue to use and then come up with our recommendations. So that's really where we're hoping to go as a key output and outcomes from this project. Next one. So a couple other places where we've tried to enhance our training is we've been using augmented reality, and I presented to this group and in other forums as well. We've developed what we call Weather Explorer. It's an app that's currently available at Google and Apple stores. That we've done a number of updates, and it basically enables you access to a variety of training that uses augmented reality, which basically brings text to life. There's videos, there's audios. You can click on various images you look at where you're just reading something in a book, and it'll actually give you some training materials in audio and video. So it augments text with other media to help you retain it better and to get more information. And the people who've used it, we've been encouraging the National Association of Flight Instructors to try to get their students to use this, and it's been well received. They're incorporating it at Western Michigan University, or trying to bring in more of this augmented reality. And it's a way of bringing things to life as opposed to just trying to read, where I think everybody's done that. You look at a chart sometimes and you see the words, but it isn't always registering, and sometimes reinforcing it by doing exercises, hearing somebody say it to you, and things like that help. We're also trying to do prototype training using virtual reality models. We're trying to see, does virtual reality in these applications provide any benefits? Virtual reality is really slick, and I'm sure everybody has come in contact with it, but it's not something that works in all places. So you'll see we've tried to develop ways of using that. And then we've also developed 10 mini weather courses that are available on multiple websites. I put the websites here. Highly recommend if you're a flight instructor or if you want to brush up, you check them out. We have a YouTube channel that has all 10 mini courses, and then we also have them loaded on Flight at 8MA. They're loaded up there. They're free. They can be downloaded, used for if you're a flight instructor, and they're also really convenient to brush up on your weather knowledge. Next one. And this is just a snapshot showing you the two of the screens that are the videos. I just put them on there so you kind of have an idea on the links and what they look like. Next chart. So I wanted to touch on with enhanced training virtual reality. We're trying to, project objective is to decrease potential aircraft loss of control on IMC. This is something we're looking at. This project is not something we funded yet. And again, I look for feedback from crowds like this to organizations to say whether or not they see. So this is a proposed project to see if virtual reality training can help reduce loss of control in IMC. So the loss of control, obviously largest cause of accidents and fatalities in GA. And even when in many cases, if weather isn't the main factor, it's often cited as a causal factor. And the project's trying to increase understanding how virtual reality training might improve pilot weather decision making and their situational awareness. And whether or not, the real thing is whether virtual reality training can do what's called recognition prime decision making. And what that basically is to make decisions more intuitive, where you're not thinking. And you can think of a lot of ways. This came about with firefighters, where they don't have time to sit there and analyze, and you basically do it on experience. I always think of it more in a sports metaphor, where if you go to make a free throw or hit a forehand in tennis, if you sit there and think what the pro told you, okay, take tennis racket back, bend wrist, follow through high, you usually aren't very good. You just pick it up. I know I'm a golfer. I once read a tip: when you write your signature, you don't practice it. You'll see people on a putting green take 10 practice strokes with their putt before they walk up there. If it's intuitive and natural, you shouldn't have to do that. So that's the idea of this virtual reality training, is can we get the experience to pilots in adverse weather and let them experience things without actually subjecting themselves to the risk. We have a neat little tool that you can actually run right now on Weather Explorer. We have a 1-minute video because talking about this stuff is a little different than seeing it. And I've actually done this training and it's really kind of slick. This just shows it. So I wanted to see if Rex can pull up this video and have it run where people can hear it. It's only 1 minute. If not, we'll let it go. But let's see if it goes. And this will give you an idea of some of the training we do.
Our Interfaces project, Iowa State University and Western Michigan University enhance weather training with 3-dimensional weather models and augmented reality technologies. Traditionally, students use text and schematics to learn about the cell cycle. The representation is limited. It is 2-dimensional and does not change over time. As part of an ongoing effort to develop AR-enhanced general aviation weather-related training, we have developed a model that represents the thunderstorm cell cycle in 3-dimensional space and over time. Here, we will launch the model in a smartphone application called Weather Explorer. The user opens the application and scans the AR marker. The weather model is generated above the marker as an interactive object in the real-world environment. Here is one 60-minute cycle at 120 times speed with precipitation. The model visualizes the cloud, precipitation, lightning, and thunder. Additionally, the model can visualize winds, temperatures, and icing. A different view helps the student learn about the cell movement across the ground. Work is ongoing to embed these AR models into general aviation weather training materials. Evaluations will assess the effectiveness of interactive AR in weather training.
Okay, that was it. So one of the things that's really slick on that, you can actually walk around with it and get on different sides of the wind models there and the cloud models and actually get a feeling, and questions pop up. And I took that training and I really didn't know much about it. And it actually was amazing how quick, when you're looking at it and you're being asked questions, you know, which direction's the wind going? And you can actually see the arrows going up, which direction, how fast does the storm typically move? And you're actually seeing it move across with measures. It really works. You get more reinforcement than just sitting there looking at a piece of paper. So we're trying to both evaluate and develop methodologies for industry to pick up to incorporate this kind of training, to enhance it, and to really gain experience in the hopes that people will recognize situations instead of having to go through where you're thinking process by process, where it becomes much more reflexive. So you're making accurate decisions, you're making them faster, and you have a recognition of the hazards much earlier and are taking corrective actions much faster. So we're really hoping these virtual reality models and the ability to get them to your average pilot on something that's free, like the Weather Explorer app, will hopefully make them accessible to everybody. So next one. Now I'm going to switch to a quick separate project that's going on. This actually is not WTIC, and I apologize because of the nature of the different projects I'm covering. There is a little bit of jumping around. One of the efforts going on in our division, though, is with ASTM, is to define minimum performance standards for weather supplemental data providers and service to UAS. They're doing weather data performance standards, weather data interface standards. These efforts began in the summer of 2020, and they're looking to complete by around the spring of 22. And basically, the intent of these groups is to enable third-party providers to do the weather that's necessary for UTM. There's a general belief that the amount of data required, and things you've heard already, especially from Matthias, when you see the complexity and the amount of data that's going to be coming in, is that the government is probably not going to have the infrastructure to do this, or the capabilities, or the dollars that industry is going to be providing a significant amount of weather. So again, like I've talked about on these other things, you need to have a minimum weather recommendation or some minimum standard that says this weather is good, this information is good enough to use in these applications. And that's what this ASTM is basically working on in these areas, to put out these guidance documents and standards to, whether you call it certify, meet, I don't know the exact term. I'm not sure they've determined exactly what you're going to call it, whether you're certificated, whether you're just qualified, whether it's like just a consumer stamp. I think those things are being worked out, but basically it's establishing the standards that have to be met so that you know that weather is good enough for use in the application you're using it. Next one. So I briefed this project a while ago. One of the projects that we still have ongoing is crowdsourcing visibility information. And I know we have a briefing coming up, and you guys have also been briefed on what we call VIA, which is the edge detection software that was developed by MIT Lincoln Labs. Well, about a few months ago, we completed a demonstration of what we call a hybrid configuration. And what the hybrid configuration includes is the MIT Lincoln Labs developed edge detection software and the selective crowd workers to produce visibility information from camera images. For those who haven't heard the briefings, the edge detection software uses edge detection, those camera images, and gives you a visibility number that should match an ASOS. Crowdsourcing, what we do is have human workers, in this case, a selective crowd of people who are both known quantities and have some training on how to do this, to provide visibility estimates and produce visibility estimates or numbers that also should be consistent with an ASOS in some cases, and I'll touch on that really quick, is that sometimes an ASOS, though by definition is accurate, may not always reflect what a pilot perceives to that number. And we've done some demonstrations along with that, and I'll touch on where that comes in here at the bottom. But so with MIT's Lincoln Labs software, what we did in this hybrid configuration is they have a trigger where they send certain images to the crowd. And this trigger occurs when the edge detection can tell that it's having some trouble determining the visibility numbers. And the crowd then provides that information as well as what we call supplementary information. We also, for the crowd to reduce their workload, implemented what we have called a change detection algorithm. So if images aren't changing and the edge detection software is sending us a lot of images, we don't want to overwork the crowd or have them needlessly look at things. So if we determine what they assess the visibility to be on the previous image or previous images, they won't have to do it, and the software will say it's the same value and put that out. We also ran an experiment to say, you know, just giving a singular number, and I'm sure most pilots have had that, sometimes can be misleading. And we've shown images where if you look straight out at the surface, you get a number, but then you can look off to a side, or you go a little above that ground level and there's low fog, or you may have certain areas around a runway that's cloudy or went into the runway. So what we wanted to do is we ran an experiment and took a bunch of these images that we got from the Alaska webcam and had pilots circle and identify, if you were looking at this yourself, what are the things you'd notice? What would be important besides just being told, you know, it's 3 miles visibility, 10 miles. Obviously, you care whether you're VFR, IFR, or marginal VFR, but there were a lot of other things they had. And this was the type of supplementary information. They said, you know, what are the sky conditions? Snow coverings could matter, the runway conditions, ceiling, the bases, and cloud top heights. And then the image detection software wants to know, are there problems with the cameras or the image? Are they losing edges? Is something in the way of the camera? Those are all things humans can do. So when we ran this demonstration, we put these tabs in there to make it available that you could produce not just a number, but identify this supplementary information to pilots, and it's in a low bandwidth form. So the plan is to hopefully uplink this information so it becomes available to pilots in a cockpit. Part of another research that you may hear Walter Combs talk about, I saw comes on this afternoon, is that we're going to be looking, he's getting access to the Starlink network for us to be able to try some things with greater access and bandwidth to satellites to pass information easier. So that's going to enhance some of the research and studies we do here. And we're going to be trying to partner with Walter and collaborate on some of our research efforts to both pass information maybe between aircraft or as well as from the ground to aircraft. But hopefully as this enhanced bandwidth and satellite communication is in place, we'll be able to use data we have and are able to produce from studies like this much easier, and to get it to pilots in the cockpit in a really simple, easy to interpret format. Next chart. So again, the findings from this were mostly that most sites show the crowd identifies the same trends as an ASOS. The crowd does a good job. Biggest difference, sometimes the ASOS give a higher value, which is kind of what you would expect in most cases because it's just shooting at the ground. And a lot of times fog and other low ceilings don't get picked up, whereas the crowd observers and even the edge detection tended to look a little broader. So you got numbers that I think were more associated with what a human thinks than what the technology says. Edge detection software, like I said, was also lower. They were more towards the crowd and sometimes even lower than the crowd. ASOS did show more extreme rises and falls over time. Assessment of individual cameras can provide a different visibility assessment from the overall site. A lot of times we put out just a site number, but there's some form of averaging or worst case, which can be misleading versus taking the cameras in all directions and actually getting an individual camera visibility number along with the supplementary information. Cloud cover information, the crowd did a pretty good job. That information appeared to be fairly accurate. The crowd also identified some potential enhancements, both for more information and ways to make the information more accurate. And then the edge detection software, we identified that there are a variety of things that the crowd can do to help it determine when it has issues such as snow cover, it loses edges, so that it can enhance its capability and get better over time. So even in the near term, as the edge detection matures, crowdsourcing seems to be a means to help it train and get better at what it does. So the prototype experiment and demo went very well, and we're hoping to run another one probably this summer with all these enhancements put in there. Next chart. We're starting up, and there isn't much to say here. As you saw, since wind is obviously the biggest cause of accidents, is also looking at the ability to crowdsource wind information. And the basic background or role of this project is to see, can we produce accurate surface wind information to enhance safety at areas where there's either a windsock or you can install one. The camera's on there, and using analytics, are we able to produce it? We did a proof of concept already on this, and the analytics that currently exist on a product that's available on the shelf are actually accurate. The other things it does, it could produce trending information and historical information, direction, speed, gusts, and things like that at locations where you don't have an ASOS and it may be too expensive to put in. If you have a camera and a windsock, it can be less expensive and you can produce this information. And our objective is to assess the capability of existing artificial intelligence technology and its analytics to do this in a manner that's cost effective and accurate. And again, going back to some of those gaps you saw, help close or reduce some of those gaps where a lack of information, and specifically wind information, was referenced as a gap in information in the cockpit. Next one. So now I'm going to move on to another quick research effort called a SkyRep. This is something, again, just to sort of show we look at a variety of ways to try to close gaps. This is being done by the PEGASAS group, which again is our Center of Excellence for GA. If you go to the next chart. So what the SkyRep is, we have a prototype done, an overview of it, is what it does is it's using imagery from the Alert Wildfire Camera Network. Specifically, they've been looking right now at the Southern California area where they have a lot of stratus and fog events. Post-analysis of images coming from these cameras provided estimates of the cloud bases and heights by assessing the vertical continuity of obscurations. And I'll have a picture on the next one. Basically, they have so many cameras there that if you look at each one at these different altitudes, you can kind of mark which camera is still below the clouds, which ones are in the clouds, and which ones are above the clouds to identify the heights and bases of these low stratus events. So, and then we did a comparison to Avail-It pilot reports and checked on the quality of the cloud layer estimates and indicated this prototype has potential to validate PIREPs as well. It may also provide independent PIREP-like observations. So it might be where you're not getting PIREPs, you may be able to get observations on cloud tops, stratus, fog, and other things that are typically really a risk from a visibility standpoint for pilots and can be hard to forecast. And the SkyReps could provide cloud-based and top information for day and night operations in regions even where you don't have many PIREPs available. Go to the next chart. This is just kind of showing where some of these cameras are, and the motivation is, like I said, in Southern California, there's a lot of these fog and stratus events. You also have mountain obscuration. So the cameras can be really useful in these regions. And this, again, you're going to hear another study I had, but you heard Matthias talk a little about it as well, is the representative of information that's not produced. You can have an ASOS, but it may or may not be representative, even if it's a short distance away, depending on the time of year and other factors. That information that isn't produced at your exact site may or may not be representative. So the cameras kind of take a different way of producing this information. And again, so far they show good promise. Next one. Next chart. Next. So this was what I was talking about. If you look at the left, these are the camera altitudes, and I think it's time across the top. But basically what you can see, if you take the line on the far left, and I can't read the numbers, but it doesn't really matter. The gray boxes say the cameras are in the clouds. The ones below those gray boxes say the cameras are below the clouds. If you look at the boxes above, obviously they're the ones above the clouds. So by doing that, you can kind of narrow where the clouds are. You can see about where the tops are, and you can see where the bases are. And it's just by people looking at these images. Ultimately, we're hoping that we may be able to use a version of the MIT edge detection to do this. Now, it wasn't designed for this specific arrangement, so there'd be some changes, but at the same time, it does have a capability to identify when it's in clouds versus when it's clear. So we may be able to incorporate this and use the edge detection for another application in regions that have this sort of camera network. And again, you know, some of the regions that have it, like Southern California, I think you'd find this could be a significant benefit in those areas with the valleys and where they do have issues with fog and stratus. Next chart. And this is showing, you can just hit it. I forgot I have this. You can kind of see, this is sort of showing how the cameras look, how you can see when you're in the clouds, when you're above the clouds, if you're below them, how that works when you do the post analysis on these images. Next one. And basically, these are some early results, things we're going to do. I've kind of addressed them already, so we can go to the next chart to save time. So another study we're doing, and this relates a little to some of the stuff you heard Matthias talk about. And this work has not started. It's been slow in acquisition, but it's going to be complementary in addressing some of the gaps we found and gaps you heard Matthias talk about. And what this has to do is provide minimum weather service recommendations, research data, and demonstrations to industry regarding the availability, consistency, and usability of weather information to address critical aspects of information representative. And the idea is information, as you move away from the source, may or may not be representative. You may use it outside a rated range. If you don't have anything better, the nearest thing may be a METAR, but it may be outside its rated range. Or in some cases, you may be within its rated range, but because of buildings, canyons, other landscaping, other structures, it may or may not be representative. And in most cases right now, people tend to use nearest neighbor, what's the closest source, and you pretty much have to assume that the closest source is the most accurate. But as we've shown, depending on the time of year, a lot of times that isn't the case, like in the Southern California region. The time of year makes a big difference on which cameras are more accurate in providing assessments, or which weather ASOS is more accurate. You can see that from the weather cameras. So what we're trying to do on this project is get a better understanding of how pilots deal with this representativeness and projection of understanding when information that's, you know, official certified, whether it's in range or out of range, how representative it may be of their area, and start building a toolbox for the cockpit that helps you address these things. So go to the next chart. So in this case, an overview is gap analyses have indicated the pilots, you know, when they have this operational uncertainty of weather information in transition settings, VFR to IMC, can cause difficulties knowing what you should use and how to determine whether or not you really have a transition. It's unclear how pilots understand this representative and a decay of representativeness as you move away from your source? Are you able to recognize what a canyon may do compared to ASOS data you're getting either 1 mile down or 20 miles? How much a METAR may actually decay as you move outside its rated distance? Traditional approaches, obviously, to rational decision making isn't a realistic model when it's this complex in a multivariate environment. And some of the things they're going to be looking at this is prospect theory and real option theory, which may be able to influence how factors on how pilots determine the risks and the decision making in these scenarios, what you do. So we're going to, again, try to put together a toolbox of ways of using maybe other sources that aren't official, tips, et cetera, to identify what may be your best representative source in the area you're flying. But the first part of this, again, is to get a better understanding of the gaps and how pilots are viewing this information and using it before we can fully try to then resolve those gaps. Next. And these are some of the tasks. I don't need to go through them. I just wanted to give people an idea of the first steps that are going to be done. We've laid out the first 3 tasks of this project. And this just is all in here for the chart, but I don't need to cover them. Next one. And that's it. As I said, my name's Gary Pokodner. This is my email. I hope, I've teased you enough that something here has caught your interest. As I said, we've got on some of these projects, we've got varieties of papers, others are new. We'd be happy to talk to you outside to give more detail. I kind of ran through a lot of projects. If there are any questions, I'll take them. If not, I get to give back about 8 minutes of time.
Not a problem, Gary. That was great, very in-depth. Enjoy seeing this move forward. I'm a huge proponent of getting more real-time weather in the cockpit for better pilot decision making. A lot of times the weather we get is static and we don't get that update on the regular basis. But as we've discussed before, we want to make sure that what we put in the cockpit doesn't become a distraction, and we don't overwhelm the pilot with too much information.
Exactly.
One of the other groups I'm working with right now that's looking at what's going on in this space is they're moving towards more of a dynamic risk analysis program. Which is really kind of cool because a lot of the risk analysis work that we do today is very static. So you do your risk analysis when you show up and then you take off and it stays the same. So they're looking at a way to pull this weather information in real time such that we have a dynamic risk analysis. So when a risk changes, it's then automatically alerts the pilot that it's either lower risk or higher risk.
Right.
And he can then identify that. So getting that information.
That's where the representative comes in that you saw from Matthias and what we saw down in the Stratus regions. You've got to know what source to go to or have a good structure of guidance that tells you which time of year to use which source, what's going to be more accurate, ways of determining which is the more accurate source to do that, and things along that line so that you know the information that you're getting real time is representative of where you're flying. And then those risks would be, are you coming to a transition where a different source of weather may be the more accurate source if you're not co-located with the source, or there's something that makes your distance, makes that information suspect.
Hey, Gary, it's Steve. How you doing? I was just talking about landing in canyons, off-site landings. What are we doing on the research regarding helicopter landing zones and weather with regard to Howie?
Well, with some of the things that are being done, that's where a lot of the camera programs are coming in. The wind one with using windsocks is directly related to some accidents that were identified by NTSB due to winds, where one of the things that happened that they know is basically one aircraft made it in safely and noticed the wind was a real issue, but there was no means to get that to the trailing aircraft. So by there's no wind sensor in the area of the Grand Canyon where this landing area is located, and it's known to be a somewhat tricky area. So that's where if we could put just a cheap and a relatively inexpensive camera in a windsock, you could identify gusts, trends, is it swirling? as well as I think when we start playing with Walter's access to the satellite network, I think those are some of the other things that we're going to experiment with. Is a lot of times when somebody goes into an area, by the time a PIREP hits, a pilot in the air has to know the PIREP's there or call in and get it. I think if you know somebody's in trail, we may be able to use that satellite network to, again, knowing what Rex said, you don't want to overload a pilot or make him, forget about flying because you give him some weather alert, but at the same time, passing information from a guy who's ahead of you in trail to highlight something that may be risky, may be something that becomes an attractive option as we get more bandwidth and these satellite data networks are in place, these commercial networks, we may be able to come up with products and ways of getting the information to pilots quicker. So I'd say a lot of the camera use is to address those items you're talking about. And then if you look at the gap chart, you'll see a couple other gaps that were identified by Georgia Tech that we haven't started yet that would address some of the things you're talking about as well that I think the pilots highlighted. And I would say Mike Splitt's study from just purely the representative information will address a lot of what you're talking about is, when pilots are flying into regions where they're further away from the source of weather information and it's hard to determine which source is most representative and are they using the wrong source. I think an ability to give them a toolbox on that could help with some of the areas you're talking as well. I don't know if you have any other, obviously you work for Pegasus, so you may know your own answer on some things I haven't heard about.
No, Gary, that's fine. Steve Cusick here. Thanks so much, sir.
Okay.
Thanks, Steve. Any other questions from the audience? If not, we'll move on to the next.
All right. Sounds good.
Greatly appreciate the information. And like I said, if anybody has any questions, don't hesitate to reach out. We're more than happy to help.
Definitely reach out. I'm going to be signing off here to another meeting, but my email, and we certainly send out, we've got a lot of reports and want to outreach. So I'm hoping this was more of a tease. And Rex, you have the charts. Hopefully they get posted. I assume you post everything so people can download the charts.
We will put everything out there for everybody.
Great. Thanks.
Thank you, Gary. You have a great day.